Hello friends, welcome to G-Centric. So in this lecture we will see problems based on the maximum power transfer theorem. Okay, so coming to this 146 question, we have got find RL for power maximum and also find efficiency. So we have to find maximum power as well as efficiency of this RL. Okay, so now if you observe this problem carefully, it is nothing but the DC case number 1. Right, this load is variable where it is a resistive network. So in that case what we had taken, RL will be equal to RS. This is the condition for P max. Right, so what will be RL? RL will be equal to 2 ohms, same as RS. Okay, so what is the power maximum formula? I square. Okay, if there is current I, this is plus minus, you can take load current into RL. So how do you find I? So I is nothing but total voltage in the circuit upon resistance, that is 4. So current is 2 ampere. So substitute in this one. In this one it will get 2 into, there is 2 square into RL is 2 ohms. So 4 into 8 is 8 watts. Okay. So this was the simple question. Okay. So you can solve it within a minute if you know the concept. Next, coming to this 147th question, you have got, okay, you need to determine the value of RL at which, okay, sorry, here also you have to calculate efficiency also, right? So what is the formula of efficiency? It is nothing but output power by input power. Right, so output power by input power. Whatever we have calculated, it is related to load. So that will become output power, that is 8 watts. So how do you calculate input power? It is nothing but the source voltage into source current, that is IL. Since it is a series network, source also it will be having 2 ampere. So that is 8 into 2. 1 by 2.5 is the efficiency. If you have to convert to percentage, you will multiply this by 100. That comes out to be 50%. So what does this mean? The power that is consumed is 50% and the rest 50% is the losses in the source resistor. So which is the source resistor? It is nothing but RS. Okay, so in that it will be 50% loss. So now using this numerical, we have seen in the theory class why do we not apply the maximum power transfer theorem to the AC circuits or AC equipments. Okay, so coming to this 147th question, what we have, determine the value of RL at which maximum power through the load. So this is the load RL and find the maximum power. Okay, so now in this type of case we haven't seen, but it is a resistive case, right? We have, there is no only one loop we do not have, right? So we have 2 loops. Now how do you solve this one? So we have already seen in the theory class of MPT that it has to be reduced to Thevenin. If you are very familiar and if you are able to solve the Thevenin circuit, then MPT is very easy. So that is why through this model only we will learn one more formula. Okay, so whenever you have got resistive network, you can directly apply that formula. Okay, so now if I consider this as terminal A and this as terminal B. Okay, so up to here it will be like Thevenin circuit. I can replace them. So I will take this as VTH and with an equivalent resistor RTH, and this will be it will be open, right? So you have to find here RL, it is open. So if I replace also, this will be RL. For time being, I can replace this with RL. So VTH, RTH and I have RL. So now it is similar to this one. Okay, so this RTH is equal to RL, right? It is nothing but source resistor, right? So this is equal to RL. Similarly, the circuit has become same. Now we have to find RTH and VTH, right? Before that, we will take the concept general formula. That is, when we have P max, okay, if there is current IL, okay, this is the current IL, P max is IL square into R. So now when I take IL square into R, how do I calculate current? It is VTH upon RTH plus RL. So when I substitute this in this, what will I get? VTH divided by RTH plus RL whole square into this is RL, right? So now this RTH or RL, I can replace it with this RTH, okay, they are equal because we already know the concept. So now this is 2 times of RTH, it becomes 4 times RTH into RTH. This also I can replace, this is square, okay, and this and 1 gets cancelled. So our result of P max will be V square TH, that is Thevenin square voltage, divided by 4 times Thevenin's equivalent resistance. Okay, so this is the important formula. But what is the limitation of this? It is only applicable for resistive network. Okay, so when we have impedance equal to resistor, okay, only it should have the resistive network, only then we can apply this formula. Okay, so now coming to this, we will solve it. Okay, so how do we solve this one? Next, we have to find VTH and RTH. To find VTH, okay, in this only I will take this RL out. Okay, so this is nothing but VTH. Okay, we have to find this one. Now, I'll take this current as, or sorry, this node voltage as V. Okay, so this node voltage I'll take as V, and this is nothing but here it is VTH. Okay, so now how do I solve this VTH? We'll take the nodal analysis, and that is the reference node. Okay, so V minus 20 divided by 5 plus V by 5, then we have got here 0 ampere current is flowing in this one, right? So what do we have? Equal to, we will not consider this one. So V minus 12 divided by, it's nothing, okay, it's 0. So this will be equal, there is no incoming current. So this will be equal to 0. Right, so we have, it is not V minus by 5 and V by 20. Okay, so this is V by 20. Okay, so we have V minus 20 by 5 plus V by 20 equal to 0. So what is the LCM? 5, 20. So it is 20 only. So this is 4 times V minus 4 to the 8, 80 plus V equal to 0. So we have got 5V equal to 80 and V is equal to 16 volts. Okay, but this is only V. What do we want? We want VTH. So how do we calculate VTH? So this voltage, this is, if this is equal to 16 volts, then if this is plus and minus, here also we will be having 16 volts across this branch. Okay, so between these two it will be 16 volts. So now apply KVL to find VTH. So it is 16 volt, then minus, this is 16 minus 12, then you have got, if this is plus and minus VTH equal to 0. So what will be VTH equal to? 4 volts, right? So now I'll rub this one, we have VTH is equal to 4 volts. Next we have to find, what we have to find? RTH. Okay, so to find RTH, for the voltage source we have to short circuit. So this is short circuit, here also it will be short circuit. Okay, so now if you observe 5 into 5, 20 and 8. Okay, so these two are in parallel and series with 8 ohms. So 5 into 20 divided by 25 plus, you have got 8. So this is 4 plus 8, 12 ohm. You have got R Thevenin also. So now R Thevenin is what? How much it is? It is 12 ohm. VTH you have 4 volts. So substitute in this one for calculating P max. So P max will be equal to 4 into 4 divided by 4 times RTH, that is 12. So it comes out to be 1 by 3 watts. Okay, so this is the question 147. So when you know the concept, okay, you have this whenever it is the resistive network, when impedance will be only resistive, then you can apply this formula directly, but you should know to apply Thevenin's theorem also. So MPT is purely like most of the questions are based on Thevenin's theorem. So if you know Thevenin's theorem very well, you can immediately find MPT. Okay, so it seems to be lengthier at the first, but as you practice on, it will be improving. The speed will be increased. Okay, so we will see a few more questions that have come in the GATE exam. Okay, so coming to this question number 148, this was asked in electrical branch in 2017. So the maximum power transfer to the resistor R is dash watts. So where is the R given? It is here. It's not at the terminal or end of the circuit, but it is in the middle of the circuit. So there will be some hint given for this also. Okay, so you should not be panicked seeing the questions. Now if it's R is here, so what is the question? We have to replace it with V Thevenin and R Thevenin, right? So this will be, and again it is the case of first one which has got resistive network. So what will be the formula for finding P max? It will be VTH square divided by 4 times RTH. So this will be replaced with VTH, and here it will be open circuit. So we are replacing this R with open circuit. Okay, so to find the VTH, that is open terminal voltage. So now this will be replaced with RTH, and this R will be here. Right, this is the R and this is RTH. So we have to find VTH then RTH. So we know that we have to reduce this to Thevenin's circuit. Okay, so now to find the RTH, okay, so I'll remove this branch. So this is nothing but open now. So here only we have to find VTH, right? So this I will take it as V. Alright, so now I can apply nodal analysis. So if you observe this one, between the two non-reference node, so this is reference node and these two are non-reference node, there is a voltage. So whatever the voltage is there, it will be super node concept, right? So if there is an ideal voltage present there, minus plus, we have got V and VTH. So in parallel with the supernode, if there are any branches, that branch can be neglected. So we have seen this concept in the while we have applied nodal analysis. So this minus will go with VTH and this plus will go with V. So this is 6 volts. So V minus VTH will be equal to 6. This will be equation number 1. Okay. So this is one equation. Next, what we have? We have to write the equation simultaneously, including VTH and V nodes. Okay, so this is VTH. I'll write this up. V minus VTH equal to 6 volts. This is equation 1. So here you will get VTH minus 5 divided by 5. Okay, so this is over. Then we have plus V by 5, and it's also outgoing current, so we will take it on the LHS itself. So there are no other nodes. Okay, so now this is LCM is 5, VTH minus 5 plus V plus 10 will be equal to 0, right? So this VTH plus V will be equal to minus 5. This is our equation number 2. Okay, so I'll write the equation number down here only. Okay, so this is nothing but minus VTH plus V equal to 6. Okay, so now I can take this as we want VTH, but it is getting cancelled. So again I will multiply with minus. Okay, so this will be minus 2 times of VTH. So this will be minus 5 and minus 6, it will be equal to 11. Okay, so this VTH we will get as 11 by 2 volts. So we have got VTH. Now we have to find RTH. So for finding RTH, we will short the independent voltage sources. So this will also be shorted, and here the current will be open. Okay. So now the current flows in the least resistive path. So this branch is neglected. So what will be RTH? It will be series of, so it will flow in, these 5 and this 5 will be parallel. That is because we have the terminals over here where we have to find the VTH and RTH and the maximum power. So this will be in parallel. So it is 5 into 5 divided by 5 plus 5, that is 10. So you will get 5 by 2 ohms. So power maximum is VTH square divided by 4 times RTH. So substituting the values in that one, we get P maximum equal to VTH is 11 by minus 11 by 2 divided by 4 into 5 by 2. So this comes out to be 5 minus, that is 121 divided by 10 into 4. So 121 by 40 watts. So this is the answer for the question. Next we will come to the 149th question. So in this case, in the circuit shown, the value of R required for the transfer of maximum power to the load having a resistance of 3 ohm is. So here in this case, this is load. Okay, so this is load, but what is our variable? R. Okay, so that is RS. So now this is the case 2 of the DC source. Okay, so now when we have the case 2 of the DC source, then it is that RS should be minimum. So minimum in the sense it can go up to 0 ohms. Okay, so now if it has to go to 0 ohms, RS will be equal to 0 and RS should be equal to RL. Okay, but here 6 into R, together they are RS. So this will be 6 plus R. So what is the value of R? It is, if it has to be minimum, then this also have to be minimum. So R you will get it as 0, right? So when you put R is equal to 0, the option for this question is 0. So directly you cannot put 3 ohm or 6 ohm. So together they make the RS. Okay, current will be flowing through this way. Next, coming to this 150th question. So this was asked in the 2011 electrical branch, and this 150th question was also asked in electrical in 2017. Okay, so now this is the AC circuit. Till now we have seen only the DC circuit part. Coming to this AC circuit, in the circuit below, the value of capacitor C required for maximum power transfer to the load is. So this whole thing is the load. Okay, so we have to find the value of C. So in this case, this whole thing load can be replaced with ZL. Okay, in this case ZL is nothing but this 5 plus. So before it is an AC network, we have to convert the inductor value and capacitor value in ohmic value. So this will be J omega L and this will be minus J omega C. So in this case, what will be omega? Here it is 100. Okay, so we will substitute once we solve the equation. Now P max in this case will be I square L into ZL, right? But what we have to find? We have to find the value of C when the power transferred in this case is maximum, right? So here in this case, RS is equal to, it has got only real part, right? In this case we have real as well as imaginary both. So in this case what we have to do, we have to compare RS with ZL, right? It should be equal because only variable part is what? Which one? We have to find the C. So RS equal to ZL, in this we have only real on the LHS. So here also real plus imaginary will be there, right? So we have to solve this, then we have to see if what part of the C will come in real or imaginary. Okay, so basically since real and real is given on the left hand side, it will come mostly in the real part. So for that we will solve the circuit given here. So how do you solve this circuit? Now this ZL, I can write it as 5, that is J omega L, after converting it into ohmic value. Okay, and these two are in parallel. So plus you will get 1 into minus J omega divided by omega C upon 1 minus J omega C. So we can rationalize the denominator, 1 plus J by omega C divided by 1 plus J omega C. Okay, so in this case you will get the ZL is equal to, I will write the direct answer for this one. So you will get the minus j omega c. This I will keep it as it is, j omega l. Okay, so plus you will get minus j by omega c plus 1 by omega c whole square divided by 1 plus 1 by omega c whole square. Okay, so this is the equation. After when you rationalize and multiply, you will get this one. So our aim is to compare with RS, which is the real part. So you see, if this is imaginary, okay, so this whole thing is imaginary and this is real part. So what we will do, 1 by omega c whole square divided by 1 plus 1 by omega c whole square equal to RS. So what is the value of RS? 0.5 ohms. Okay, so now you can simplify this one. You will get this as 1 by omega c whole square plus 1. Okay, so this will be equal to 0.5. Cross multiply, you will get 2 is equal to and omega c square plus 1. So 1 when it goes over there, you will get 1 equal to omega square c square. So we have seen omega value is 100. Okay, before that we want c square, so 1 by omega square, c will be 1 by omega, 1 by 100, this will comes out to be 10 millifarad. Okay, so when you know the concept, easily you can solve this one. So RS here, ZL is variable. When ZL is variable, it will be RS is equal to ZL. Okay, so this is the case of the AC thing. So in the next lecture, we will see few more questions based on maximum power transfer theorem. Then we will switch on to the reciprocity or Milliman's theorem. Okay, thank you.